Today we are going to look at the average value of a function and then talk about the mean value theorem for integrals and look at what that looks like. And what we know is that the average value of a function represents its average height, if you will. So if we look at this area under the curve, and let's call this area under the curve here, from A to B, then if we look at an average height of this, the average height might be something like this, if we draw the line across, and we'll just call this the average height. Okay, well, what we know about the average value for a function is that geometrically what we have is that there is a rectangle that we just drew with the same endpoints that represents the same area under the curve that the curve does. Meaning this area here in blue, let's draw it in blue, this area of this rectangle here is equivalent to the yellow area under the curve. Okay, well, let's talk about area and how we would calculate the average value. Well, we know how to find area, correct? If we find area, to find area, we would do base times height of a rectangle. And in this particular rectangle, my base has a dimension of b minus a. And then the height is that average value that we're finding, right? So that's the height from the, in this case, the x-axis up to that average height. So this is equal to the area. Now, let's solve for the average height. And solving for the average height, we would divide by this b minus a term. So we get that the average height is equal to the area divided by b minus a. Okay, well, tell me what we know about area. Well, hopefully what we know about area, because we've been doing it for the last few weeks, is that area is represented by the integral from a to b of the function f of x dx divided by the interval that it happens on from b to a. This is what we call my average value. Okay, we can see if we scroll and look at this formula, that this formula says the average value of f of x on a to b equals f of c, which equals the area of the region, so that integral from a to b of f of x dx, and the width of that region. Actually, what I like to say is this is the integral divided by the interval. Integral divided by interval is the average value. You can also see it written another way with this 1 over b minus a on the outside of that integral, and that makes sense. It's the same thing. Okay, well, let's look at an example of this. Okay, if we want to find the average value of f of x equals x cubed minus 3, sorry, it doesn't say that, x cubed minus x on the interval 0 to 2, and we want to do it without using a calculator. Well, what I'm going to do is I'm going to use that average value function that we just talked about, that the average value equals the integral from 0 to 2 of x cubed minus x dx divided by the interval of 2 minus 0. Okay, well, let's work on this. Using antiderivatives, we would get that the numerator is x to the 4th over 4 minus x squared over 2 evaluated from 0 to 2 divided by 2. So my average value is this. Now let's simplify that. If we plug 2 into the numerator, we would get 16 over 4 minus 2 squared is 4 over 2 minus 0 over 4 minus 0 over 2, which gives me, 4 minus 2, not sure why I wrote that, divided by 2 equals 1. So my average value is 1. Now if we look at this on the graph, if I look at the average value of 1 on the graph, here is my average value. And so the area of this rectangle is right here. Now remember that area of that rectangle is equal to the area under the curve in that same interval. Well, keep in mind that area under the curve in the same interval includes a negative portion as well as this positive portion. And what you can see is that those two areas are actually equal. Now, the mean value theorem for integrals says that if we have this continuous function and we find the average value, then there has to be a c value on that same interval where the function is actually equal to the average value. Now, we have a nice visual with this graph right here because we can see where the c value should be. That c value should be right here, where the average value is equal to the actual function. And so if we're going to do that, what the mean value theorem says is that the average value has to equal the function evaluated at c. So let's find that value. So we would have x cubed minus x equals 1, because that was our average value and our function. Now I have two ways I can do this. In my graphing calculator, the first way that I could do this is to let x cubed minus x be y1 or y2 and 1 be y2 and find their intersection point. The other way that I could do this is I could subtract the 1 over, so we get x cubed minus x minus 1 equals 0. And then I would let this equal y1, and I would find the 0. So either way, take a second, hit pause, and see if you can find the x value, or in this case the c value, that gives us the average value of 1. All right, hopefully you had a chance to go through and do that, and you got that x equals 1.325. Now, does that fit the idea of where that point should be, or what we see on our graph? And what we can see on our graph is, yeah, that makes sense, that is approximately 1.325, where the average value equals the function. Okay, consider the velocity function v of t equals 6t minus 0.3t squared meters per second, graphed below for 0 to 20. First question says, what is the displacement? Well, let's think about what displacement means. We know that displacement means it's the area under the curve of the velocity function. And we happen to have the velocity function. So to be able to calculate the displacement for this, we are going to take the integral from 0 to 20 of 6t minus 0.3t squared dt. And if we take the integral of this, we get, let's go up a degree, that'd be 3t squared minus, go up a degree, we'd get 0.1 t cubed. And we're evaluating this from 0 to 20. So using the fundamental theorem, we'd get 3 20 squared minus 0.1 times 20 cubed minus, well, that will be 0 minus 0, so we're good there. So here we get 1200 minus 800, so we get 400, and with the units on this, if we're talking about displacement, would be meters. Okay, but then the question says, what's the average velocity? What is the average velocity? Well, what I'm actually trying to find is the average value. So I'm going to take the integral, you know, the one we just calculated, divided by the interval. So really I have 400 meters. I already did the legwork up there, so we're going to leave it there. 400 meters divided by 20 seconds, in this case, is what t represents. So we get the average velocity is 20 meters per second. Okay, so let's draw that on the graph just so we can see what we think. If we were to draw the average velocity, we'll do this in blue, do the other average in blue. So first let's look at the area under the curve. So if we look at this area under this curve, we'll pretend I got it under the curve. And we sketch this area under the curve. And if I go through then and say, okay, if I take a rectangle of that same interval, and I calculate the area of this rectangle, it will be the area of that curve. And we can see that. Visually, we can see that probably that this area right here that is not under the rectangle, if I sum these two pieces here, these triangular looking pieces, they would probably, or they will be equal. So let's review. Let's go back to when we were talking about derivatives. The mean value theorem for derivatives said if a function is continuous on a to b and differentiable on a to b, closed interval a to b, open interval a to b, then there is at least one point c in that open interval at which the slope of the tangent equals the average slope, the average rate of change. But the mean value theorem for definite integrals says that if a function f of x is continuous on the closed interval a to b, then there's at least one point c on that closed interval at which the function value is equal to the average value. So here we have the average rate equal to the instantaneous rate, and here we have the function value equal to the average value. Okay? And that's the mean value theorem for definite integrals and and derivatives. Okay, so using that idea and what we just looked at, that last example, there's actually two different ways we can find average velocity. And it's pretty common for the AP test to put position, velocity, and acceleration problems on their test. So it's not a bad idea to think about how they are related. So let's say you're given a position function, okay? And they ask you to find your average velocity. Well, if we're given a position function and asked to find the average velocity, this is going to be delta x over delta t, the change in x, the change in the position over the change in time, which we would say is algebra 1 slope. So if we know the position function, we can find the average velocity by finding the average rate of change. Because if you're given a position, velocity is the rate. All right. Now, if you're given the velocity function and we want to find the average, then what we're going to do is we're going to do the average value, the integral from a to b of the velocity function over the interval from b to a. Now, if we take the antiderivative of the velocity function evaluated from a to b, what do we get? We get the position function evaluated from b to a. And what do you notice there? We find the average velocity, whether it's through position, if we're given position, or whether we're given velocity, we found the same formula. They're the exact same. Okay? So remember, if you're given position, then velocity is a rate. So if we're given position, velocity is the rate. It's the rate of change. But if you're given the velocity, then the average velocity is an average value. Keep that in mind. Okay, so that's just a pretty quick synopsis of average value of a function, and then the mean value theorem for integrals that we use. So I hope you have a great day.